Okay, so this is just going to be a little introduction into inference with means. Remember, inference is when we are using what's true for a sample to try to estimate what's true about a population. So we're going to talk about that today, but just as an introduction before we get into the actual lesson and examples, I want to talk about a guy named William Gossett. So William Gossett lived from 1867 to 1937. He worked for Guinness, the Irish beer company, not Guinness World Records, and his official job title was quality assurance. But basically, he was a statistician who used statistics to help the company make sure they were creating the best tasting beer. So, in essence, he kind of used statistics to kind of test batches of beer and then see whether or not it passed a certain standard. And he used hypothesis tests and confidence intervals to do that. He published a lot of papers while he worked there regarding statistics and the things that he found out. But for a while, we didn't know who he actually was because he used the pseudonym Student because Guinness didn't want their employees to publish papers using their own name. So for a while, his theories and methods and all of the stuff that we're about to talk about were under the pseudonym The Student. So I thought that was interesting. So what Gossett, or The Student, discovered when he was doing his tests, so he taste tested batches of dark lager in very, very, very small sample sizes because, alcohol. Don't want to be drunk at work. He set his level of significance, his alpha, so that he should only be rejecting good beer about 5% of the time based on the parameters that he set up. So that's his type 1 error rate, or alpha. But later he found out he was actually rejecting good beer closer to 15% of the time, which is obviously a big mess up. So what he realized is that with small samples and more unknown variables, the normal model, actual normal model with its very specific equation, doesn't work quite as well when we're dealing with numerical data, small sample sizes, with some more unknown parameters. So what this means when we're dealing with numerical data is that we have to change things up a bit. So this is a standard normal model. We call it the Z distribution because we use a Z table for it. It looks like that. So if we had a perfect situation, we would always use the normal model. But instead of using the normal model for these types of problems, we use what we call, or they called for a while, the student's T models, or the student's T distribution. Now the T distribution looks a little bit different. It is much shorter in the middle and it is much wider on the sides. It is still symmetric, it is still unimodal. So we might call it normal if we were looking at it just with our naked eye, not really thinking about it, but it is much shorter in the middle and much more long and spread out on the sides than an actual normal model. So they're more spread out, there's more area in the tails. And the reason for it being so much shorter and so much wider is because we're using a sample standard deviation to estimate a true standard deviation. So remember, in any inference problem, we're using the sample data to estimate the population data. So there's always some amount of uncertainty, but we can usually deal with that. But on a means problem, not only are we dealing with using a sample mean to estimate a population mean, we now have this extra layer of uncertainty because we're also using a sample standard deviation to estimate population standard deviation. So there's an extra layer of uncertainty or variability, which leads to the graphs being created from these to be a lot more spread out. There's more area in the tails and less area in the middle. And that makes actually a big difference when we start talking about error and power and p-value, and all of those things are a lot different when we're dealing with these technically different models. And then beyond that, the other thing that the student, or William Gossett, discovered was that depending on the sample size and some other things, but mainly sample size, that distribution might look a tad different. So again, this is our standard normal model, or Z distribution. This is a T distribution that has what we call 20 degrees of freedom. Degrees of freedom is based mainly on sample size, but it also in some situations depends on other things For a one sample means problem, which is what we're going to talk about today, degrees of freedom is just simply n minus 1. I'm not even going to go into what degrees of freedom actually means and where that term comes from, because that is a topic that is not worth spending our time on right now. But for a t-distribution with 20 degrees of freedom, which means the sample size is 21, it looks a little bit like that. Whereas a t-distribution with 10 degrees of freedom, so a sample size of 11, is even shorter. So the smaller the sample size, the shorter that graph gets in the middle and the wider it gets on the side. So the smaller the sample size, the more uncertainty that there is. Oops, I did not mean to click that, but there is a little link here. I'll try to put it in the cards so that you can see. It's another crash course video that talks a little bit more about degrees of freedom and what it is. So if you're curious about that, I will link that. So when do we use a T model instead of a normal model? This is kind of what we want to know. So basically what it comes down to is we use a T distribution or a T model to solve a problem when we don't know the population standard deviation, which is honestly going to be most of the time in a means problem. So when we're using the sample standard deviation to estimate the population standard deviation, right, we have the extra layer of uncertainty, so we need to use a T distribution to kind of handle that extra uncertainty. Basically, this is going to be pretty much always, like I said, for a means problem, because in real life, when are we just going to happen to know the population standard deviation? If we don't even know the population mean, and we're using an interval or a hypothesis test to estimate that, why would we happen to know the standard deviation? So it's just kind of one of those things where it's like pretty much always. Other things that are good to know about the T distribution, these like to come up on multiple choice questions. One is that there's more area in the tails, like I mentioned earlier. They're more spread out than the normal model. Secondly is just to know is that as degrees of freedom, just based on sample size, so as degrees of freedom increases or as sample size increases, that T distribution is going to look more and more and more and more like the actual normal model. And in fact, a T distribution with infinite degrees of freedom, which is not really realistically a thing, but technically, theoretically, a T distribution with infinite degrees of freedom would look exactly normal. So the bigger your sample size or degrees of freedom gets, the closer that graph is going to look like a normal model. Okay. The last thing I'm going to talk about in this little intro is how we can use what we call the t-table to find different values that we might need to calculate a confidence interval or a p-value in a hypothesis test. So I'm going to open what we call the t-table. I will make sure and link that to this little intro video and in the in Schoology main folder. So let me open that. All right, so this is what we call the t-table. So it looks like this. You'll notice we still have this kind of graph at the top that shows what it's telling you. If we look at this table, we have along the top degrees of freedom. So that this left-hand column is the degrees of freedom. And then up here we have what they say is the tail probability P, which is basically the probability above a certain T star or T critical value. So in essence, what's happening is each row represents a different T distribution based on a specific degrees of freedom, just based on sample size. So in essence, we could have, remember our Z table was this, right? This is for a normal model or Z distribution. We basically have like a whole bunch of pages and like a full table full of numbers. I could potentially have an entire Z table for each row of this T table. I could have an entire Z table for every single degrees of freedom or sample size that I'm interested in, but that would be a huge waste of paper and space. So they've condensed this down majorly to where each row represents one T distribution for specific degrees of freedom. So how we read this. So let's say I was doing a confidence interval and I need to know my T star critical value, like Z star, but for T, for a problem where the degrees of freedom was 10. So what I would do on my table is I would, of course, go to degrees of freedom 10, right? I would look at that row. Now I could look at the tail probability. That's where we're going back to, remember what we talked about with Z-star, where if I want, 95% in the middle, and there's 5% left over, but that 5% is split between the two tails. So one tail will be half of that, just 2.5% or 0.025. So I could use that top row to find the tail probability and then match it up with the degrees of freedom. And there's my T-star. Now, the other thing that you can do is on the very, very, very bottom row, which is actually on the second page of that table, they actually give the confidence levels also. So I can see that 95% confident is the same column as the tail probability 0.025. So you can look in either place. Of course, then I would have to go up to the first page and find it for degrees of freedom 10. So that would be my critical value, my T-star, if I were calculating a confidence interval. And then I can do the same thing for part B, n equals 20. But remember, degrees of freedom is what I have to look up on this table. For a one sample problem like we're doing today, degrees of freedom is simply n minus 1. So sample size 20 minus 1, which is 19. So I would look at my degrees of freedom 19, still 95% confidence, so we're still looking at that same column where the tail probability was 0.025, and we get a T-star of 2.093. Okay. One thing I wanted to mention is if you got a degrees, notice that this table, it goes up to degrees of freedom 30, and then it starts skipping. And then at a certain point, it's not going to do every single degrees of freedom because, again, we don't have infinite paper to put this on. So if you had a problem where the sample size was 45, so your degrees of freedom is technically 44, there's not a row for that. The rule is if there's not a row for the degrees of freedom, you're always going to go down to the next sample size below. Remember, sample size is going to affect the width of the interval. So we never want our interval to be too narrow. So if we don't have a row for degrees of freedom 44, we'd rather our interval be a little too wide. So we're rather going to go down to the next lower sample size just to make sure that our interval is going to be as accurate as we want it to be and that it includes the answer. So we'd rather it be a little bit too wide than a little bit too narrow for what our sample size is. So that is the rule about degrees of freedom if there's not a row for it. The other thing that we can do is we can estimate a p-value given a certain value of our, instead of z-score, it's t-score, but we can estimate a p-value. Now this you won't have to do nearly as often. We are going to use calculator to do pretty much all of these tests. Critical value comes up a lot more on multiple choice than p-value does. But just so you know how to do it, your p-value is going to be estimated. So let's say we had a problem where the degrees of freedom was 8 and the t-score, which again is like a z-score, I'll talk more about that in the main lesson video, is 2.75. So what I would do is, again, I would find the degrees of freedom 8 row, just right here, and I would look in that row where I have some these are possible values of t that we could get. And what I'm going to do is I'm going to find where 2.75 would fit in this row. So obviously I'm not going to see, or usually I'm not going to see an exact t-score that I'm looking for, but I'm going to find where 2.75 would fit, which is between these two numbers. It's between 2.449 and 2.896. So 2.75 is somewhere between those two values. So now I'm going to look at my top where my tail probabilities are. And what that tells me is that my p-value is going to be somewhere between those two tail probabilities. So for a t-score of 2.75 and degrees of freedom 8, I know that my p-value is going to be somewhere between 0.01 and 0.02. So it's not super specific, but it is enough for us to still write a conclusion, because if I know the p-value is between 0.01 and 0.02, if my alpha is 0.05, well, I know my p-value is less than that. So I can still say I reject the null and all that stuff. The other thing, part D here, if n is 16, so degrees of freedom is n minus 1, so degrees of freedom would be 15. If we get a t-score that's negative, Your t-table only gives you the positive side, but remember this is symmetric, so the negative side will be the same area, the same tail probability. So I can still just look up. So if I'm going to look up degrees of freedom 15, my t-score is negative 1.23, I'm just going to look for positive 1.23 because I know that tail probability on the other side is going to be the same. So degrees of freedom 15, t equals 1.323. So I'm going to find where that fits, which is between these two values. It's between 1.074 and 1.341. So I'm going to go to the top. That tells me my p-value is between 0.10 and 0.15. So again, I could still use that to write a conclusion because that's a pretty big p-value. It's probably going to be bigger than alpha. So we would fail to reject the null. So that is how we use the table. This is not something you're going to have to do too often. We are going to use the calculator to get exact p-values or to get exact intervals, but occasionally this will show up on multiple choice questions, so it's good to know how to use the t-table. So that's it for a little intro. I know that was kind of long for an intro, but the next video goes more into the actual process of doing a hypothesis test and confidence interval for this type of problem, for means. All right.